Okay, hello everyone. My name is Michael Downey, Library and Information Services Coordinator at the AWRI, and it's my pleasure to welcome you to today's webinar and also to welcome today's presenter, Dr. Paul Petrie. In February this year, Paul joined the AWRI and SARDI in a new joint viticulture scientist role. Now, prior to this, Paul was the National Viticulturist at Treasury Wine Estates, based at Penfolds McGill Estate in Adelaide, and has also been on the board of the ASVO and was president there for 3 years until 2014. Now, it's been a couple of years since Sonia Needs presented a webinar on frost management strategies, so we're fortunate to have Paul with us today to provide a timely update. But before I go to Paul to tell us more about today's topic, just quickly a couple of notes on what you can expect from the webinar. The format is a short PowerPoint style presentation followed by a Q&A. The session is being recorded and will be available to view via the AWRI website. And finally, for those that are new to webinars, it's important to remember that webinars are interactive and there are a number of ways to get involved. To ask a question, please type into the questions section of your control panel in the bottom right corner of your screen. And for those with access to a microphone, there is also the option of speaking directly with the presenter by clicking the raise hand button. This is located in the top left section of your control panel. If you'd prefer to ask a question via email, please do so at infoservices@awri.com.au. Please send your questions through at any time, and once we get to the Q&A, I'll get as many questions through to Paul as possible. And finally, if you want to get involved through Twitter, please use the Twitter handle @the_AWRI. Okay, that's enough from me. I'm now going to hand over to Paul to tell us more about today's topic.
Thank you, Mark. Thank you, Michael. So first to start up, why are we all here? Research out of the grains industry is showing us that the frost season length is increasing. On the map that I've just put up on your screen, the blue sections are the area where there is more frost or a change to the frost season length between the 1960s and 2010. This is due to a southerly shift in the band of high pressure that normally sits over Central Australia in spring, and is an interesting contrast to the earlier budburst that we would normally expect to see with climate change. So basically, we should be expecting our frost risk to increase over time. Likewise, the Bureau of Meteorology has recently announced a El Nino event. This also comes with increasing frost risks due to reduced cloud cover and lower rainfall and soil moisture, giving us, or the reduced cloud cover gives us lower night temperatures in winter and spring, and once again a greater frost risk. If we look at El Nino seasons in places southern New South Wales and northern Victoria can experience 15 to 30% more frost days during El Nino compared to the historical average. So I'll now cover off on the different sorts of frosts. These sheep look pretty cold, don't they? Pretty miserable out there. There are two types of frosts. This is an advection frost, and it can occur during either the day or the night. It's caused by a large-scale movement of freezing air, normally coming off polar regions, and is generally associated with moderate to strong winds and a mixed atmosphere. So there's not the same gradient in air temperatures. Temperature of the entire air mass is normally below 0 degrees, or well below 0 degrees, and this is, I suppose, it's fairly difficult for us to manage in a vineyard or any sort of horticultural crop. Fortunately, these types of frosts normally only occur during winter time, and they're not really a major issue for frost management in Australia. The other sort of frost is a radiation frost. This is much more typical of what we would have trouble with in spring. It only occurs at night, and it's caused by long wave radiation cooling from the earth to the sky. So these arrows here going up from the soil. So during the daytime, we get energy from the sun that heats the soil and warms the soil. Then at night, this energy is released. The frost risk occurs under calm, clear, and dry atmospheric conditions, because if we have cloud cover, basically the cloud acts as an insulation and keeps that heat in and prevents the frost occurring. The temperature will is coldest closest to the ground and will increase as you move upwards. And this is sort of frost that's generally a problem for vineyards in spring. So here's a diagram of the inversion formation that occurs over a night when we're getting a radiation frost. We see about 4 o'clock. We have the temperature here. So it's fairly similar from the ground going into the sky, and nice and warm, above 10 degrees. As the sun sets, the temperature starts to cool and the inversion starts to develop. So we now have at 8 o'clock cooler temperatures near the ground, still above zero, but then warmer as you go into the air. And as the night progresses, this intensifies. So by midnight and then 4 a.m. in the morning, we have temperatures below zero at just above or a bit above the soil surface, and then as we move up beyond sort of 2 meters, 4, 6, 8, 10 meters into the sky, the temperature goes above zero, and we see that sort of classic inversion layer. Once we get to 8 a.m. and the sun comes out, then the profile changes again and you get some more heating close to the soil surface. During inversion events, the air is relatively still, but you still can have some air movement, and I'll sort of cover that a little bit more further along in the presentations. And I will also come back to this again when we talk about methods for managing frost. Okay, so this is a whole lot of fancy-looking physics formulas, but I'm not going to run through these in a heap of detail. That's for sure. Basically, because this is these radiation frosts are driven by physical events, they're relatively easy for us to forecast. So this is an example of not the graph, which is quite complicated, but just this. The instructions up the top here is an example of a formula that was developed to help forecast frost, or the chance of a radiation frost in New Zealand. It's based on it's forecasting the grass minimum temperatures, the temperature at the soil surface, based on the temperature at 3 p.m, the dry bulb temperature, and then the calculated dew point, and a constant. And basically what it's saying is that if we know the temperature at 3 o'clock, as the heat is radiated from the soil, then by the time we get to dawn, or the cold just before dawn, the coldest part of the night, we can work out what temperature we'll get down to. The Bureau of Meteorology does a pretty good job of forecasting frost events over most of the country, but certainly if you're in a region where you're feeling that maybe the frost forecasts don't always reflect what occurs on your site, you could use a technique like this to try and forecast the chance of having a frost effect or a frost event. And I'd be happy to work with anyone who wanted to put something like this together. Would also be important to have a reasonable range of temperature measurements, or a reasonable long run of temperature measurements, and including frost events, to demonstrate that this sort of formula was working, because you wouldn't want to make a decision based on something like this and then run into trouble because you hadn't put your frost management plan into action. Yeah. So another, I suppose, interesting effect that you often see when you have a frost event is that not all the shoots along the cordon are damaged. Now, if we look at the photo over on the right there, we can see there's a couple nice green-looking shoots sort of sitting out amongst the damaged shoots that are likely to have not been affected by frost. So I was intrigued by this. These undamaged shoots are protected by a phenomenon called supercooling. For ice to form, it needs a nucleation site. So this is often a piece of dust or some bacteria or some other sort of flaw in the water droplet that allows the start of the ice crystal. It's a similar phenomena that we see that also initiates the start of the bubbles in the sparkling wine glass, and it's the same mechanism that is used to protect buds before they start to burst from freeze damage. Another analogy or another way where you may have seen this sort of thing occur before, if it's a really cool day, a really hot day, you may have put a can of beer in the freezer to cool down quickly. If you leave it a little bit too long, you get it out, and the beer still it still sort of rattles around in the can. You know that it's still liquid there, but as soon as you open that beer, then it freezes solid because the release in pressure has allowed the bubbles to start to form, and they act as a nucleation site in the beer freezes. So the protected shoot is like the can of beer that hasn't been opened, whereas all the frozen shoots are the cans that have the bubbles inside and that have all frozen solid. Yeah. I'm now going to run through some of the different types of frost management or different frost management options. So first, I'm going to talk about passive management options. These are the sort of operations that you can do in your vineyard to help prevent frost. Things like site selection, managing air drainage, ground cover, soil moisture, cordon height, and delaying budburst. I will then go on and discuss some of the more active options for frost management, so things like using water, wind machines, heaters, and other potential frost management methods that you may or may not have considered, but also some of which have sort of less or more likelihood of being successful. So without wanting to sound too much like a real estate agent here, like site selection is really all about location, location, location. We all know of, or I'm sure we all know of, vineyards that are located in less than ideal sites. So we talk about sort of frost pockets. These are low points in the topography where the cool air ponds and collects, and basically are at the highest risk of frost. We also, with altitude, the temperature decreases. So if we look at the top of a hill up here, this is also a cooler position than midway down the hill. So really, if you're looking or have the luxury of being able to reposition or choose a new vineyard site, then this would be the sort of area you'd want to target here, the sort of the halfway down the hill. Management options can also impact on the air drainage and the air movement. This phenomenon of cold air movement or cold air drainage is called katabatic airflow, and it basically relies on the cool air being denser than the warm air and therefore flowing down the topography as water would run down the topography. If, for example, you have a hedge or some sort of shelter belt located on the downhill side of your vineyard, then the cool air can pond behind this hedge or shelter belt and create an artificial frost pocket. So the removal of these sort of things can aid and can certainly reduce your frost risk. Likewise, if you have the opportunity, you can install some sort of either a tree line or other sort of barrier to air movement to try and divert the cool air around your vineyard site, and this can improve the temperature of the vineyard, or can be a a supplementary method, or can support other frost management, more active management strategies, things like wind fans or frost pots, which I'll talk to in a little bit more detail. Also, knowledge of these sort of airflows can be really useful for situating things like wind fans. So soil or soil temperature management is one of the main opportunities that a vineyard manager has to help manage frost. I presented the top row of this diagram earlier, and it shows that, you know, with clear soil, clear soil, that during the day the soil absorbs heat from the sun and then radiates that heat out at night. If we place an insulating layer across the top of that soil, so this is something like a layer of straw is a really good example, but it can also be any sort of cover crop, mulch, or even cultivated fluffy soil. This prevents the heat storage or accumulation during the day, so little heat is stored, and then it also locks that heat into the soil at night, and it prevents its radiation. So basically the soil is cooler at the end of the day and then isn't able to release as much heat at night, and this increases the risk of frost quite dramatically. I looked, when I was preparing this presentation, I tried to find some tables on the insulating value of different sort of ground covers, and I wasn't able to find anything that was really good, but there would be an opportunity to sort of try and benchmark some of the different ground covers and some of the ground cover treatments that you can put in place. So, for example, how much of a reduction in frost risk do you see from rolling a cover crop as opposed to mowing a cover crop, and those sort of management opportunities. A couple of weeks ago, I got sent this a flyer for the Australian Cabernet Symposium. It's going to be held in Coonawarra on the 15th of October. And while I'm certainly excited about the symposium and hope to be able to attend, I was even more excited about the really neat picture that they had on the bottom of the flyer. This is a great example of the impact of cultivation on frost risk. We can see the centre of that row has been cultivated, and that nice fluffy soil has acted as an insulator. So the dew that's settled on there is frozen and given you that lovely white, that row of white crystals down the middle of the row. On either side of the row in the undervine area, it looks like there was there is a little bit of grass or something growing, but maybe that's been grazed down quite short, or it's been herbicided and it hasn't come away, and that soil's provided much better insulation and has really prevented the frost occurring on those that undervine zone. Soil moisture is also really important in the effectiveness or how effective the soil is as a storage heater, how well it can store the heat that it absorbs during the day. We talked initially about the increased frost risk with the El Nino, and certainly going into a spring without a full soil profile increases your frost risk. So what does water do for what does soil moisture do for frost risk? Well, it improves the thermal mass of the soil and also the heat conductivity of the soil. So thermal mass is a term that describes how much heat the soil can store or absorb, and then the heat conductivity is how far the heat from the sun can penetrate down into the soil profile. So if we have a moist soil, a soil that's at field capacity, over the course of the day, the soil can absorb heat down to approximately 30 centimetres, whereas if we have a dry soil, really it doesn't go down. We're lucky if it goes down half that far. Obviously, the soil type and the density of the soil would drive these relationships too. But generally, if we have a moist profile, especially that first 30 centimetres, the soil can absorb more heat during the day and then release that heat during the night as a frost control mechanism. Okay, cordon height. as I said earlier, the temperature is lowest at or just above the soil surface, and it increases as you move up, first through the canopy and then well above the canopy. This can be quite a steep gradient, especially really close to the soil surface. So if we look just down at the bottom of this graph, that's the 2 metre line there, so 2 metres above the ground, and we can see that there's a really steep gradient here of temperature increase as you move away from the soil surface, to the point that you can get up to a half a degree difference between a cordon that's located at 0.9 metres and a cordon that's located at 1.4 metres. And I appreciate there's other management options or other management issues that are associated with raising your cordons up that high, but from those of you that know me would be well aware, I'd be quite happy pruning a 1.4 metre cordon. I reckon that sounds like a really good height. Delayed pruning. So obviously as the buds burst, they become more susceptible to frost damage. And I'll put up a table of how that changes on the next slide. If you can delay your bud burst, then you can effectively give yourself a buffer when frost is less likely to impact on your vines. This photo comes from a trial that I ran in the Barossa sort of 3 or 4 years ago when I was still working at Treasury Wine Estates, and it shows the difference in shoot development that you could get by on the left-hand side was pruned during winter, and then on the right-hand side was pruned when the shoots were 5 to 7 centimetres long, and it gave about a 2-week delay in bud burst. So basically it extended the season when you weren't at risk of frost by a couple of weeks. I suppose there's a couple or a few caveats here. One, we pruned late, but while the vines were still in dormancy. So we had an early white vines in dormancy and a late white vines were in dormancy treatment, and we didn't really see a very big delay in bud burst due to that later pruning. So to be really effective, the pruning needs to be done post-bud break. And obviously if we're delaying the phenology at the start of the season, then that delay in phenology is likely to carry through to the end of the season. So you can see a delay in maturity, and you'd want to be wary of this technique if you were using it in a cool region where you may get into trouble with rainfall or the break in the season and the lead up to harvest. If we look now at the sensitivity of buds to frost damage or to air temperature and their stage of development, these results came from Pinot Noir. Most of the results I could find on this came from Labrusca varieties, so information out of North America. But so this was really the only good vinifera results that I could see, and it does appear to change between variety. And as we would expect, freeze sensitivity increases as the shoots develop, and the threshold for damage was around -1 degree during that early part of the season, sort of shoot burst first and second leaf. But while you were once you got beyond that, so the fourth leaf and onwards, it was a little bit lower, maybe only -0.6 of a degree. The temperatures required to damage 50% of the shoots were quite a lot lower, but if you're using an active management strategy, I think you'd probably want to go for the no damage threshold. So that provides a good opportunity to move on and talk now about some of the more active management strategies. If we start off with wind machines, I'm aware of quite a number of new wind machines that have been put in the last couple of years in response to recent frost episodes. They were first developed in the 1930s in California, and they normally target a start time or a start temperature of around 0 degrees. Wind machines rely on that inversion that I gave you or showed on the that I showed previously. So the height and the strength of the inversion is really critical to their effectiveness. these parameters will change season to season and night to night and location to location. So certainly having a wind machine isn't a guarantee that you can manage a frost. And before you turn that wind machine on, you want to ensure that the temperature at the top of the wind machine's tower is indeed warmer than the temperature at the bottom of the wind machine's tower. I have heard anecdotal stories of people turning wind machines on and actually causing frost damage around in the zone where the wind machine was having an effect, as opposed to preventing frost damage. So the mechanism the wind machine uses is fairly simple. Basically, it mixes the warm air that's higher up in the atmosphere with the cold air near the ground, and makes a more uniform and closer to average temperature for the profile. Helicopters work on a very similar method to wind machines, so they rely on that inversion layer and mixing the inversion layer. Helicopters, I suppose, have a little bit more flexibility in that they can target inversion layers that are higher up in the atmosphere, or if you have enough helicopters and confident enough pilots, you can stack the helicopters, so one helicopter will push the air down to the next helicopter. Their their popularity varies a lot between regions, but certainly in somewhere like Marlborough, New Zealand, they're very popular, to the point that they worry about running out of aviation fuel, petrol to make the helicopters go if they have a series of frosty nights in spring. You want to ensure that your helicopter pilot is confident and certified to fly at night, so they can avoid things like the Stobie poles and tree lines and that sort of stuff. And I note the power poles in the background behind that helicopter in the photo. One of the techniques that the helicopter pilots or the Vineyard managers use to aid with the location of the helicopter is to have a light linked to a thermostat located on the top of some of the Vineyard posts. So the light is set so it flashes red when it is below 0 degrees, or below negative half a degree, whatever their critical threshold is, and green or yellow when it is above those temperatures. And so then it is relatively easy for the helicopter pilot to see where the temperature is decreasing too much, and can target those parts of the vineyard for the helicopter. That might be especially critical if you're getting air movement across the vineyard, and so the air that has been mixed is then moving through the vineyard site, and you can really just target the upstream edge of the airflow for the mixing. Okay, so next up is heaters, or oil or gas heaters, or smudge pots as they're commonly called. So these work while the previous methods I've described rely on mixing that inversion layer. These work, heat the plants using a different process. Basically, they heat via convection, so it's the movement of the warm air created by the oil or gas heaters. And so effectively, you're trying to warm your entire vineyard, and to do that, you need quite a lot of heaters. It depends on the temperature and how rapidly the temperature is decreasing, but it is in the order of about 100 per hectare to be effective. A low inversion layer that said, a low inversion layer does help with the use of these oil or gas heaters, because effectively you can set up a cycle, so the heat is convected up from the heater, then goes up and hits the inversion layer, sits there and cools and drops down, and basically makes a cycle under the inversion layer that helps you maintain a a warmer temperature in the vineyard. Basically, you're not trying to heat heat the whole atmosphere. If you have fewer larger heaters, then you have to be careful, because you can generate so much heat that it basically punches through the top of the inversion layer, and then that heat is lost. So even heating, and so fewer smaller heaters is better. Likewise, if we see some people use strategies using bonfires or something like that to try and ward off frost in their vineyards, they will leave a pile of prunings to burn during the frost season. And one point source of heat is going to be a lot less effective than heat evenly spread through the vineyard. Yeah. So sprinklers, the start temperature, or the temperature when you turn the sprinklers on, is normally targeted around 1/2 or 1 degree, and this is done to get the system up and running and up to pressure before you have any issues around frozen lines, especially with the flipper type sprinkler system, so the systems that don't attempt to water the whole vineyard. Those temperatures do change. The recommended start temperature is higher with, decreases at higher relative humidity, and there are tables available to help you calculate those, and I can provide some more information on that if anyone is interested in using those. As for the temperature when you usually turn the sprinklers off, a rough guide is that it must be above freezing, and you want to see the temperature rising, so a definite increase in temperature before you turn them off, because as soon as you stop that the sprinklers, then the risk of frost damage returns. Basically, you need to keep putting that water on to keep the vines protected. Application rate and the frequency of application are key drivers to the effectiveness of sprinklers. So the top graph on the right shows the same amount of water being applied, but with sprinklers that have different return cycles. So a sprinkler that rotates every 30 seconds compared to a sprinkler that rotates every 120 seconds. See, the 30 centimetre return time the 30-second return time provides much better protection. The temperature only drops to just under -1 degree Celsius compared to a 60 centimetre return time, which gets down to -2, or a 120-second return time, which even goes probably a little bit below that again. Likewise, the amount of water that you need to put on will vary with the minimum temperature that you have to protect against. So you could get to the situation when you have a very cold frost that your sprinkler system doesn't put out enough water to protect against that frost. And I suppose the setup and the calibration and the running of that sprinkler system needs to be designed around the minimum frost temperature that you're looking to manage. Some of the existing system, or that said, some of the existing systems can apply water, I suppose, a little bit too generously, or can be set up for frost events that are very unlikely to happen. And so it would pay if you have a sprinkler frost protection system in place and you haven't done this, to go and look at its application metrics and try and balance those against the coolest frost that you've ever seen in your vineyard site, to see if you might be able to realise some water savings or some pumping cost savings. Under vine sprinklers, under vine sprinklers, as in used in irrigation, can provide some protection against frost, but it's certainly not to the same level as the over vine sprinklers. So they use some of the same same mechanisms of the over vine sprinkler. So when the water lands on the vine, it freezes, and energy or heat is released as part of that freezing process, and that provides protection against it maintains the temperature of the shoots and the protected foliage. while that occurs directly on the sensitive foliage for the overvine sprinklers, for the undervine sprinklers, that heat would then need to radiate up into the canopy. So even at those, at an equivalent water application rate, the undervine sprinklers aren't likely to be anything near as effective as an overvine sprinkler. Okay, so I'm going to talk about some of the, I suppose, less conventional frost management or frost control methods now. This is a report out of some trials run at the University of New England, looking at heated cables, sort of a little bit like the wires inside your electric blanket, except running out down the row in the vineyard, and they saw reasonable effectiveness for these heat cables in the particular frost event that they investigated. So you can see the inflorescence damage or inflorescence loss was reduced by the use of the heated cables. As the heated cables are generally wrapped around the canes or around the cordon for the spur pruned vines, their effectiveness only extends, or doesn't extend all the way up the canopy. So, and I suppose protection of the inflorescences are the most important part of the vine for protecting the yield for the following season, because even if the tops of the shoots sustain some damage, then they can grow out or come away again. Another technique that has been developed or investigated is artificial fog. So this is fog created from water, and it's effectively creating clouds to prevent or to provide insulative cover to the vineyard. So when I was first sort of introducing the topic of the radiation frost, I said we don't normally see these on cloudy nights because the clouds provide insulation, and so effectively the fog provides insulation. You can also get some added benefits of the fog condensing and then freezing on the shoots, so this provide protection in a similar manner to the overvine water sprinklers. This is a relatively uncommon method. Really, it hasn't moved far beyond I suppose the research concept, mostly because the logistics of it are fairly difficult. You need a very high pressure water supply. You need very clean water, because the emitters that produce this very fine fog are prone to blockage, and you need very fine sprinklers. And there are also issues, especially in places like the US, where there's concern if this artificial fog was to run over a roadway, for example, and cause a car accident, would there be some public liability problems? Okay, so last up is sprays and different sprayed-on preparations to help manage frost. So there's I suppose a couple concepts that are used here. There are bacteria that can live on grape shoots and that can provide nucleating sites, so effectively increasing the susceptibility to frost. So they provide a nucleating site for the freeze to start occurring. These can be killed by copper sprays and potentially allow supercooling to occur. These have been shown to work in a lab situation. However, it's a lot more difficult, or it has been a lot more difficult to demonstrate their effectiveness in a vineyard. There are a lot of other things, dust, for example, that can also provide a nucleating site for the frost and allow damage to occur. So, as I say, it's been difficult to show how effective these are. There are also other products or applications that claim to provide a protection against frost. Often these claims are based on an improvement in osmotic potential of the plant, so basically more sugar in the plant, and this can reduce the plant's freezing point. Once again, that it is very hard to demonstrate the effectiveness of these treatments in a vineyard, in a field situation, and I would encourage anyone who's looking at using one of these techniques to leave an untreated section in your vineyard to really see how effective it is. Okay, so that pretty much concludes my presentation, and I can ask for questions now if anyone has any.
Great, thanks very much for that, Paul. And as Paul's just indicated, we will move through to a Q&A from here. So start sending your questions in. Just a reminder, you can type your questions into the the bottom section of your control panel. You can also use your microphone and click the raise hand button, and you can also email in your questions.
Okay, so I've got a question first up. Do I know of anyone who has done any work trialling anti-transparence as a frost protection measure? The answer is no. I'm not aware of anyone that has actually trialed these products, and I suppose similar to my caution around the around the products that improve the that improve the osmotic potential of the plants. I haven't seen any really good work that shows that these products are effective, and especially effective in a vineyard situation. And I would encourage, if somebody was going to trial these, that they leave a section of vineyard or a row or a portion untreated, so they can actually see for themselves whether the product has been effective or not. Okay, so the next question is: there's been quite a lot of frost fans established in the Barossa this year due to the frost that occurred in spring of 2014. Sort of quite large numbers, maybe even between 40 and 70. Do I think that this could impact on the airflow and direction, causing damage to other areas that have not been affected in the past? So normally when we think of barriers or potential barriers to airflow, we talk about things like shelter belts and tree lines, or even artificial raised barriers to try and to change airflow, or airflow that's due to changes in topography. Are the frost fans likely to alter the route of that airflow? My best guess would be that no, they wouldn't. However, they may change the temperature of the air that is moving, and this could work. This could conceivably work in both directions. If you were on the downhill or the downstream side of a frost fan, you could, I suppose, potentially actually get some benefit from that frost fan, and that the air temperature of the air moving through your vineyard would be increased. However, I'm sure there would be situations where vineyards that had been, sites or where air that may have been available to one frost fan, the inversion has basically been moved or been disrupted by the frost fan upstream, and that means that the potential to raise temperature isn't quite the same further down. So the next question is: has any analysis been done on the undamaged shoots to see why they weren't damaged? I don't think any detailed analysis would have been done on the undamaged shoots, because it would be quite hard to sort of show that those shoots didn't have a nucleating site for the freeze damage. So if possibly if you could have a thermal camera in the vineyard and watch as the shoots freeze one by one, and then you could try and pick and say, well, why hasn't this shoot frozen yet compared to the next one along? It's most likely, as I said, due to lack of nucleation sites, but because there's so many potential nucleation sites, and effectively as soon as you touched or banged that shoot or tried to probe the shoot, you would likely provide a nucleation site and allow it to freeze. I think it'd probably be quite difficult to do that as well. Okay, so the next question is around different foliar sprays that may increase the elasticity of cell walls to provide a benefit or reduce frost risk. So I'm, I suppose, generally fairly nervous about any of these spray-on products and how effective that they are likely to be in a vineyard situation. There are some that have been shown to be effective in more controlled environments in a lab, but I say it's very difficult to show how effective they are in a vineyard. And all I can do is repeat what I said earlier. And if you are looking to try and use one of these products to leave a control section in your site to see if it was really effective. Okay, so the next question is around vertical fans. So these would normally be fans that were mounted, would sit on the ground as opposed to up in the air. And then I asked sort of how effective are these likely to be? I have seen some of these used, or I've helped trial some of these fan systems here in Australia, and I've also seen some used in New Zealand. The company that I saw supplying them provided quite a detailed analysis and quite a detailed system about where the fans needed to be located and how the how this would impact on air movement. With any of these things, I mean, similar to the spray-on products, it is very hard to demonstrate what the effect would have been if you didn't have the fan in place, and likewise to sort of measure the strength and the height of the inversion and under what conditions those fans are likely to be more or less effective than the conventional size fans. I had to say that the conventional fans appear to be the benchmark that everybody uses, and that'd probably be I suppose the safer option. Okay, so the next question is around using vine guards on new plantings in frosty areas. Should the guards be applied after the frost season, and are some guards better than others? So this is actually, I think I might take this question on notice if you don't mind. There's a couple factors that could be at play here, both around sort of the guard protecting the shoot from frost damage, the guard promoting shoot growth earlier than it would be otherwise, and also making the plant more susceptible to frost. And so if you're okay, Marty, I'll come back to you and maybe have a bit more of a chat about that once I go and do a little bit more investigation.
Okay, that's all the questions we have at this stage, Paul. Thank you to everyone who sent through those questions. Before we start to wrap up, did you want to make a final comment there, Paul, or do you have? No, okay. I think we'll start to finish then. Okay, Firstly, thank you to Paul for coming in and presenting today. And thank you to everyone who's joined in and attended and being part of today's session. For attendees, you will receive a follow-up email with a link to the recording of this session. And you also receive a link to a survey. Should you need to follow up anything from today's session, please feel free to contact the AWRI directly. Next week's webinar will be presented by winemaker Toby Barlow from St. Hallett, and the topic is juice flotation, a better winemaking tool than cold settling. If you haven't already registered for this session and would like to do so, please visit the AWRI website. Again, thank you to everyone for logging in today, and please do join us again